The second member, this second member would annihilate or kill or do away with or make 0, whatever you wish to call that, annihilate polynomials of degree 1. Essentially, sequences of the form some say q 0 plus q 1 n, q 0 and q 1 are constants. What I mean by that is the following. If you look at the overall sequence being given to the filter bank at the input, and if you think of that sequence as possessing one component of this kind and the remaining essentially a residual component, only the residual component would come out on the high pass branch. This polynomial component would only be present in the low pass branch. So, the other way of saying it is a few more smoother terms are retained on the low pass branch and removed from the high pass branch. Another way of saying it is, well, the high pass branch becomes even more and more high pass. So, what I am saying effectively is that it really behaves more as a high pass filter than does the case of Haar of length 2. Daubechies of length 2 is the Haar, and that does not behave as well as a high pass filter as does this. In fact, I would like to put down 2 exercises for the class now with this discussion that we have had, and I strongly recommend as a part of this course that students work out both of these exercises to understand what I am saying. Working out these exercises does mean using a computer. It would help to use a computer to evaluate the expression finely, to get a good feel. It can't be done by hand, but it is worth doing. So, the exercise is as follows. I shall explain the exercise here. Exercise 1. Work out the iteration. To move towards the Daub 4 as they call it. This is a nomenclature that we would like to introduce here. Daub 4 means the Daubechies filter bank with the filters of length 4. So, here what we have just been talking about is the Daub 4 set of filters or Daub 4 filter bank. So, we have already explained how to carry out the iterated convolution, but it would be worth actually carrying it out to move towards the Daub 4 scaling function. One would notice that the function that emerges is a continuous function, but it would not be expressible in what is called closed form. So, one would not be able to express it as some sin t or sin e raised to the power t or something of that kind, but it would be a continuous function. It would converge to a continuous function. Now, this is something important here. We have just set up some kind of a filter bank and we have started iteratively convolving the impulse response with its own compressed versions. What is it that guarantees that when you carry this iteration to infinity, there is going to be some semblance of convergence in that process? Nothing inherently. So, if we take an arbitrary filter bank like this with an H 0, H 1, G 0 and G 1, and if you were to take the H 0 and carry out an iterated convolution like this, you might land up with what is called a fractal function. In fact, when I say fractal function, the word function is a misnomer. It would mean that that iterated convolution process would not converge to a function at all, or at least definitely not to a continuous function. That could very well happen. In the Haar case, we had a neat, beautiful rectangular pulse to which it converged. In the Daubechies 4 case again, we are going to converge towards a continuous function, I am assuring you, even before you carry out this exercise. We will soon see that for the higher order members of the Daubechies family, you would again converge to continuous functions. However, if you just picked some arbitrary low pass filter and started iterating it like this, maybe even a low pass filter which satisfies that orthogonality to even translates that we have asked for. There is no guarantee that any such arbitrary filter would converge in this iterated convolution. So, what is it about this filter which allows convergence? In the literature on wavelets, they speak of this as a property called regularity. So, we say that the filters need to obey for the iterated convolution to converge. Converge to what? Well, converge to a function which is either continuous or at least continuous almost everywhere, except for an isolated finite number of points. So, if you really want to look at it that way, the Haar scaling function is not continuous, but it is only 2 points at which it is discontinuous, not an infinite number of points. And we do not want that situation of this iteration taking us to a quote unquote function or object which has infinite points of discontinuity. That is what we are trying to say. So, whatever it be, this regularity in this case comes from the presence of zeros. So, one guaranteed way of forcing regularity is introduction of factors So, the more zeros you have at z equal to minus 1, of course, in the low pass filter, and therefore, correspondingly you would have zeros at plus 1 in the high pass filter. Again, to give a physical significance, when you put z equal to minus 1, you are talking about e raised to the power j omega being equal to e raised to the power j plus minus pi. So, omega being equal to pi, the extreme frequency, extreme high frequency. So, in the low pass filter we are saying put zeros at the extreme high frequency, and correspondingly therefore, in the high pass filter we put zeros at the extreme low frequency, namely 0, omega equal to 0. Omega equal to 0 corresponds to z equal to plus 1, e raised to the power j 0 is 1, simple. So, one way to force regularity is to put zeros at minus 1, and that is what we are doing in the Daubechies family. Haar 1 0, Daub 4 2 zeros, Daub 6, that is the next member of the family, length 6, would have 3 zeros, and so on and so forth. And you know what we say? We say the higher you go in the Daubechies family in terms of length, the more regular your filters are, the more regular. What that means is, the functions to which we converge on iterated convolution become smoother and smoother. They have more and more derivatives that are continuous. So, if you look at Daub 4, its differentiability in the traditional sense is under scanner. It is continuous, but as far as differentiability goes, there are issues. But when you go to higher order Daubechies, that is also taken care of. So, the functions become smoother and smoother. And now, you can see how to do this for higher order Daubechies filters. I mean, whether it is length 6 or length 8 or length 10, we know exactly how to carry out an iterated convolution. Put all those impulses together, the impulse response coefficients as impulses uniformly spaced, squeeze that set of impulses by a factor of 2, convolve it with the first set, again squeeze by a factor of 2, convolve it again, and this can continue and continue and continue. So, I leave it, as I said, as an exercise to complete this iterated convolution. So, I repeat the exercise which all of us must do, work out the iterated convolution to move towards the Daub 4 scaling function. The second exercise which I would like to ask the class to do is the following. Obtain the frequency response of the Daub 4 low pass filter. And of course, therefore, also of the high pass. So, just for completeness, let me write down the expression for the frequency response. What I am saying is, obtain H 0 plus H 1 e raised to the power j omega plus H 2, well, e raised to the power minus j omega, H 2 e raised to the power minus j 2 omega plus H 3 e raised to the power minus j 3 omega. Evaluate at many finely spaced omega. So, maybe between 0 and pi, one could take 1000 points and evaluate this expression to get a feel of the frequency response. And the idea is to compare it with the frequency response of the Haar. So, what we are specifically looking for is this. Haar gave us essentially this cos omega by 2 kind of response between 0 and pi. In Daub 4, are we going closer to ideal? What ideal are we talking about? You remember what the ideal was. The ideal was essentially this. This is the ideal, an ideal low pass filter with a cutoff of pi by 2. Now, let me tell you how to build the next member of the Daubechies family. To do that, then we would put one more 0 at z equal to minus 1 in the low pass filter. The next member of Daubechies family. Essentially, take H 0 z to be of the following form: 1 plus z inverse the whole cubed, and there would be 2 more degrees of freedom now, or you could call it B 0 tilde if you like, just to distinguish it from the B 0 that we have calculated here. B 1 tilde z inverse. Remember that this member would have a low pass filter of length 5, of degree 5 and therefore length 6. And since it is degree 5 or length 6, 3 of the zeros are constrained, 2 of them are free. So, you have 2 free parameters here, B 0 tilde and B 1 tilde. And what are the constraints in this case? The constraints are the non-trivial ones, orthogonality to translation by 2 and 4. In other words, let me put it down explicitly. You have H 0, H 1, H 2, 3, 4, 5. Translation by 2 would mean this. The rest of them are 0, so we do not need to bother. Translation by 4 would mean this. So, take the dot product of these two and put it equal to 0. Take the dot product of these two and put it equal to 0. These are the two constraints. So, I will read them off. H 0 times H 2 plus H 1 times H 3 plus H 2 times H 4 plus H 3 times H 5 is 0 in this, and H 0 times H 4 plus H 1 times H 5 is 0 in this. And these are the only two non-trivial constraints that we have. Two constraints, two free parameters, one can determine them. Simple quadratic equations, this time they are simultaneous quadratic equations involved, little more work, but doable. And one can keep doing this for higher and higher order members. Now, by the way, there are different ways of building this family of Daubechies filters. This is one way. There are more convenient ways too, or what might be seen as more convenient by some. It is not our objective to dwell on those methods in this lecture, but rather to make a more general remark now about this class of filter banks that we are talking about, namely the conjugate quadrature filters. So, we wish to put down what we call the minimal requirements of design in a conjugate quadrature filter bank. Incidentally, you might wonder where this name comes from, conjugate quadrature. Actually, it is the quadrature word which is important there. The quadrature word comes in some sense from the idea of a 90 degrees shift. So, in a certain sense, what we have done is to relate the high pass filter and the low pass filter frequency responses by a shift of pi on the frequency axis. So, notionally what we are saying is a low pass filter with cutoff pi by 2 aspires to become a high pass filter with cutoff pi by 2 in this relationship. replacing z by minus z essentially. So, this replacement of z by minus z to relate the low and high pass filter brings what is called a quadrature relationship. That about the name. But anyway, so what we have is essentially the following equation. The principal equation governing the quadrature filter bank is this. Kappa 0 z plus kappa 0 minus z is a constant, where kappa 0 z is h 0 z, h 0 z inverse. And therefore, if you look at it, the frequency domain says kappa 0 e raised to the power j omega is h 0 e raised to the power j omega, h 0 e raised to the power minus j omega essentially. And with a real impulse response, what do we have? With a real impulse response, we have mod h 0 e raised to the power j omega squared is kappa 0 e raised to the power j omega. So, in other words, now we have a very clear design problem before us. Designing a conjugate quadrature filter bank is equivalent to designing essentially one filter, kappa 0 e raised to the power j omega. So, the design problem is design kappa 0 e raised to the power j omega. And if you look at kappa 0 e raised to the power j omega, it is a non-negative frequency response, as you can see. Mod h 0 e raised to the power j omega, the whole squared. And this non-negativity can only come from an even, a real and even response. So, we are saying kappa 0 z corresponds to a real and even impulse response. The constraint that even samples must be 0. Except the 0th. So, you know, this equation that we had here, kappa 0 z plus kappa 0 minus z is a constant, essentially says the even samples other than the 0th sample are all 0. So, you are trying to design a low pass filter. So, in fact, we should qualify this further, non-negative low pass frequency response. And what kind of a low pass frequency response? With a cutoff pi by 2. So, now we have the design problem very clear. Design an even impulse response, a low pass aspiring to be a low pass filter with cutoff pi by 2, non-negative, with the constraint that the even samples of the impulse response are 0 except for the 0th sample. There are many different ways in which one can design finite impulse response filters, and any optimization which allows us to design kappa 0 with these constraints is acceptable to design kappa 0. And once we have kappa 0, then you look at its roots. For each root, you have pairs of reciprocal roots H0z, H0z inverse. Out of each pair of reciprocal roots, put one in H0 and the other one automatically goes to H0z inverse. So, this is a general strategy to design conjugate quadrature filters, and the Daubechies family is just one of many such families. So, with this then we have put down a whole family of multi-resolution analysis or filter banks for you. In the next lecture, we shall ask what is it that we are looking for in these families. In other words, is there some fundamental limit, is there some fundamental two domain requirement that we are trying to seek and fulfill. Thank you.